Hello everyone. In this video we are going to talk about shortest path problems. So basically based on the properties of the graph and also actually the question, there are different versions of the shortest path problem. Whether the graph is weighted or unweighted, whether there is a negative weight in among the edges of the graph or not, whether there is a negative cycle in the graph or not, whether we are looking for single source shortest path. It means you started from a node finding the shortest path to all other nodes from this node, or you are looking for the shortest path among all of the pairs. So basically based on these different, the answer to these 4 different questions, we can have different type of problems and so different algorithms to solve them. Interestingly, if your graph is undirected or directed, it's not really going to change the algorithms. So I'm going to discuss the algorithms, the problems and the algorithms over the graphs which are directed, and which is actually more difficult than undirected. If you have an undirected graph, just modify the algorithm simply and they work over the undirected graph as well. So the first type of question, shortest path problem that we have is over unweighted graphs and a single source problem. So the thing is, you are going to find the shortest path from a node to all other nodes in the graph in a connected graph, which is unweighted. The answer is you can run the BFS. We have already discussed this property of the BFS tree, that for all the nodes that you will see, the distance from the starting point is going to be minimized if there is no weight over the edges. So the cost of each path is going to be the number of edges on the path. So what would happen if we add some weights to the edges over the graph? Is the BFS going to give me the optimal answer? So the short answer is no. The BFS is going to fail if you have a weighted graph. For example, if you have a graph like this, starting from the node A, the BFS is going to give you the distance from A to B is just actually using this edge, so the cost is going to be 4, although you can see that here, if I go from A to C and then from C to B, the cost is going to be 3. So over the weighted graphs, the cost of each path is going to be the summation of the cost of all the edges along that path. So although the BFS is going to fail, in this case, it's not going to give me the optimal shortest path, the minimum shortest path. But still the idea of the BFS might actually help us. Kind of the idea here is something similar to the idea of the minimum spanning tree, the prime algorithm over minimum spanning tree. Remember, in the prime algorithm, you started from a node and you just grow the tree, right? By adding the edges, the minimum edge, just growing the tree by adding the minimum edge and always just visiting a new node that you haven't visited before. Basically, the idea behind this algorithm that I'm going to discuss here is exactly the same. You started from that the source node that you wanted to find the shortest path from that node to all other nodes in the graph, and you visited the first node which is connected to this node with the minimum edge. but you are not going to actually visit the whole graph. So in the previous example that we had, this graph here, let me just erase these drawings. Okay, so the thing is, when we started from our source node A, you don't visit B and C both at the same time. What you do is you visit the node which is connected with the minimum edge. So A has 2 edges going out and the minimum one is 2. So basically from A you visit C and you choose C, but you don't, it's just like B will remain in the queue. So you would actually keep a queue. You add A, and then you, at the beginning A is there, then let me actually erase here. A is in the queue. You remove A from the queue, okay, and you push the both nodes C and B to the queue. You keep them, but the one that you actually remove is the one with the minimum distance, or the edge that is connected that with the minimum distance, which is going to be C. So C will be removed from your queue, okay, and for C, what I'm going to do, I will add all the nodes which are connected to C, like E, D, and B. So the point here is that you can see that B have been already added to the queue. In the regular BFS, you wouldn't add B again, right? Here what we do is that because we are visiting B through 2 different actually points, you can either visit it through this edge from C, or you can visit it through A through this edge. So we keep some number which actually shows the distance from the starting point along with each node inside the queue. So it's just like for B, you will keep a value like 4 that shows the cost of this edge that connects B through this edge to A, right? And then later on, if you visit B again, because you are going to visit it through a different path, the cost of it is going to be a different cost, right? It might be more or less. So if it is less, if the cost of visiting B through a different node is going to be smaller, you would update the cost for B. So it's just like in this case, the cost of visiting B through C is going to be 3. So what would happen is that this cost will be updated, and you actually update it to cost 3. So B in the queue will remain in the queue, but the cost of visiting that will be updated. And also we are going to add the other nodes that can be visited through C, which are going to be the node E and the node D. And associated to each one, you are going to add some cost that, for example, the cost for visiting E is going to be 7, and the cost for visiting D is going to be 6. Okay, and then in your queue, it doesn't matter, in the regular BFS, you would remove the next node from a regular queue. Here, from this list of nodes that I keep here as a queue, I don't actually care that when the nodes have been pushed to the queue, have been enqueued to the queue. I will find the node that has the minimum cost, which here happened to be B, right? So in the next step, what would happen? The node that will be removed is going to be B. So the node will be removed, the node B, but the thing is, it will be removed because it has been visited through C, not because it has been pushed to the queue from A, right? And then by adding the node B, what would happen here is that, let me actually remove it from the queue. You through B, you might actually see some other nodes. Again, you can see that the nodes D and E are already in the queue, but because I can visit them through a different path, I should update all the weights. They might actually find a better cost to visiting them. For example, for the cost of visiting the node D through B is going to be 5, right? The cost of B, which was 3, plus the cost of this edge that actually connect B to D. So the cost of D will be updated. It's going to be, 5. And there is also a chance that the cost of E will be updated. So let's just see, if we visit E through the node B, the cost of E will be 6, and you can see that it is less than the cost of the E, which already we have. So you should update this cost as well. So the cost of E is going to be, oh, I should have used that. 6. And then the node that will be removed from the queue this time is going to be the node D, which has the minimum cost. So you can see that the idea is exactly the idea of the BFS. We just modify that so that in addition to actually keep the nodes that we can visit, we also actually keep the cost of visiting that node, and we remove the node from this queue based on that cost, not based on the order of visiting the nodes. So this is the whole idea of this algorithm that let's just actually apply. This is the algorithm. You can see the algorithm is written here. I have just actually modified the BFS. So what I'm going to keep is that cost of all the nodes that I have actually have discussed here. These costs, we are going to keep them in an array that we call it the distance array, or you can actually just write it as D of E, that for example D of E will be equal to 6. D of D will be equal to 5 or something like that. Okay, so this is the algorithm. At the end, for the single source shortest path problem, just one thing that here I assume the cost of the edges are all positive. I will talk about it, that what would happen if there is any edge with cost negative to this algorithm, but so for now, just assume that the cost of all the edges are going to be positive. So for this single source shortest path problem, starting from the node S, we are looking for the shortest path from S to all other nodes. Okay, so clearly when the cost of all the edges is positive, the shortest path, all the edges that you are looking for is going to create a tree for us, right? That's why I'm actually just showing it here as a T, that at the beginning only S is there, and I have an array for all the nodes that shows the distance from the from the source node S. At the beginning, the cost of the distance of all the nodes is going to be infinite, except S, that we actually assign 0 to that. The cost of reaching from S to S is going to be 0. And we are going to also keep that array of parent. This P, this array P, is going to just tell me that from which node you have visited the node. So in this way, you can, by just following all the nodes and their parent, you will create the complete tree that shows the single source shortest path tree. So the parent of the starting node, we set it as null. For the rest of them, they will be assigned based on the cost that we have. So at the beginning, we only from the any starting node S, the nodes that you can visit are going to be all the nodes of that are connected to S, right? So for all of these nodes, let's just call them V. For all of these nodes, you update the distance based on the weight of the edge S and V. We call it W. This is a function that tells me that what is the cost of this edge from S to V, and the parent of all those nodes will be initialized as S. Okay, so basically it's just telling me that you are visiting V through S. And we are going to just continue. You can see that this version of the algorithm doesn't use a queue. I'm going to just discuss that why we need a queue, and basically we need a specific form of a queue. We need a priority queue to run this algorithm because we are going to always find the item with the minimum cost. Okay, so while we haven't covered all the nodes, while T does not cover all the vertices, you always find the node which is not a part of the tree, you haven't visited yet, the node with the minimum value of dv, basically minimum distance. You add it to the tree, and if the okay, for all the edges that they are not a part of the graph yet, they haven't been visited before, you just check if the cost of V plus this the cost of that edge is going to be smaller than the, for example, some situation like this, that you have a node like X. Okay, it's just telling that, or for example this situation, this node X have been already visited through S, right? This situation is just checking that if the cost of d of x, the previous d of x, is greater than the cost of visiting V plus the cost of visiting x through V, this edge of V and x. So in this case, you will update the cost for this node. D of x will be the cost of D of V plus the weight of this new edge V and x, right? And you update the parent of x as well. So the parent of x will be equal to V. So what is the time complexity of this algorithm? You can see that I basically intentionally write the algorithm in this way to show you that if we don't use a proper data structure, the cost of finding, always searching for the item with the minimum distance, minimum value of the D, is going to be N. So in total, the cost of this loop is going to be O of N power 2, which is going to be too much for these costs. What we can do here is even actually more than N power 2, because you are checking all the edges here. It might actually be the cost at the end will be N to M, the total cost of this loop. The whole loop here, which is going to be too much. But the thing is, instead of just using a regular array, we don't have a good data structure here. I can use a priority queue. Using a priority queue, always in the while loop, we can actually always ask the priority queue to give me the item with the minimum cost of D. Okay, and you know that removing from a priority queue, from a regular binary heap, actually is going to cost O of log of n. And in total, we are going to have at most n a number of nodes in the queue, right? Each time. Basically, each time you're going to remove one item, so it's going to be even smaller than that. So we can say that in the worst case, the time complexity of removing an item from the queue is going to be O of log of n. But there is some other cost that you should be careful about it, and that is the cost of updating the nodes. In the case that you are actually visiting a node through some other node, you are updating the cost of it. You might actually update the cost, right? And you know that there is some methods for changing the value, the key in a priority queue, the item which is already in a priority queue. And the cost of that is going to be log of n over the a regular binary heap that if we actually store it as a complete binary heap. So in total, the time complexity that we have here is going to be how many times you might update the nodes. This is going to be m for each edge. It is possible that you update the cost of one node, right? So in total, you might actually update, you might call this decrease key function for m times the cost of it is going to be O of log of n. So in total, the time complexity is going to be, and basically because the whole thing is inside this loop of n, the total time complexity is going to be n plus m2 log of n, which is basically can be written as m log n, because usually actually m is bigger, right? One point about this algorithm, which is basically the Dijkstra algorithm, this algorithm that we already actually discussed is called Dijkstra algorithm for the finding the shortest path over a graph with all the edges are positive costs. The thing is, the main cost that we have for the Dijkstra algorithm is the cost of updating the key in our priority queue. We know that updating the key in a regular, in a binary heap, something that we have actually discussed in COMP359, updating the cost of a node in a binary heap is going to be the cost of percolating up the node. So that cost is log of n. But there is another form of a priority queue. If you implement it using the Fibonacci heap, instead of binary heap, you implement it using your Fibonacci heap. If you implement it using the Fibonacci heap, the cost of actually updating one node is going to be constant. So in that case, this cost here is going to actually decrease a lot significantly, and instead of getting m2 log of n, basically you are actually remaining with the cost of log of n inside this loop that will be n2 log of n, just the cost of popping an item. So you are you're actually just getting rid of the cost of updating updating the distance over the nodes inside your priority queue. So the total time complexity will actually reduce to n log n instead of m log n. Okay, this is definitely way better, because usually the number of edges is more than the number of nodes. The number of edges, you know, that can be actually up to the number of nodes power 2. So you might actually now ask that why we don't usually use the Fibonacci heap. The point about the Fibonacci heap is that it takes more space than the regular binary heap, that we can actually store it in just simply as an array. The Fibonacci heap, you have to store it in a tree and it takes a lot more space. But it is more efficient in terms of some of the cost of some of the methods, like updating the keys, this decrease key. And in some algorithms like Dijkstra algorithm, if you don't care about the space that much, you can actually use a Fibonacci heap and get a more efficient algorithm. So in total, if you are asked what is the time complexity of the Dijkstra algorithm, the time complexity is going to be O of n log m plus m. Basically, you have to actually keep this m, and the reason is that we are visiting all the edges, and if the cost of the edge, the number of edges is equal to n power 2 or close to that, this one is going to be more than n log n. That's why we have to keep both of them, both of these two terms. So the cost of the Dijkstra algorithm is n log n plus m. So this example here shows basically how we run the Dijkstra algorithm over this graph. So I'm going to just quickly go over this because we have already seen that. You actually keep an array like D. The value of all the nodes at the beginning is infinite except A, which is the source node. Then by visiting actually all the nodes connected to A, the cost of B and C will be updated to 2 and 4. So basically these are these edges. And then you get the node with the minimum item. If you look at all the nodes D, E, B, and C, you will see that C is the minimum item. So the next node that will be visited is going to be C. From C, you will update the cost of B, the cost of D, and the cost of E. And then the next node will be B with the minimum cost. From B, you will update the cost of D and the cost of E as well. And you will next remove, cover the node D, which has the minimum cost. And from D, you cannot update any other node. And then the last node that will be visited is going to be E. By keeping all those edges, you can see that the final result is exactly look like a tree. It started from node A, you go to C, from node C you visit B, from B you visit D, and you visit E. Okay, so let's run the Dijkstra algorithm over this directed graph with all the weights which are positive, starting from the node A. So I'm going to just keep track of those arrays for D, the distance, and also the parent. And these are the nodes A, B, C, D, E, F, G, H, and I. Okay. So the cost for all the nodes are going to be infinity except the starting point, which is 0. And the parent of A is going to be null. Okay. And let's just mark the nodes that we visited. You check the priority queue and you remove the item with the minimum. You create a priority queue and you put all the items inside your priority queue, okay? And you remove the item with the minimum distance from your priority queue. Priority queue is going to give you A here for the first time. So A will be removed. The cost for A is going to be 0. And through A, you have 3 edges corresponding, actually the cost of all those nodes connected to the node A can be basically updated here, right? So the cost of B will be updated to the cost of A plus, the distance of A, which is 0, plus the cost of the edge, which is 15, and the parent is going to be set to A. The other node is C. The cost is going to be 13, the parent is A. The other node is D. The cost is 5, and the parent will be set to A. Okay, so the next node that will be removed from your priority queue based on this distance D is going to be the node D with the cost 5. So the node D will be removed, and okay, along the way I'm going to just show you that which part of the graph this single shortest path tree has been actually created. So this edge is going to be added to the tree. Through the node D, you can visit 2 other nodes, E and I. The cost of both of them can be updated. The cost of E will be updated to 9. The parent will be set to D, and the cost of I also will be updated to 104. 5 plus 99, and the parent will be set to D. Okay, then you check the priority queue and you remove the item with the minimum cost. If you check the priority queue, you can see that the next node with the minimum cost is going to be E. E with the cost 9. So this node, this edge, and this node will be added to the tree. Okay. Through E, you can update F, you can update G, you can update I, you can update C. So I'm going to go through them one by one. The first, let's actually see the node C. The cost of E is 9. 9 plus the cost of visiting C through E to C, which is going to be 3. The total cost here is going to be 12. It is less than the cost of the already cost of 13 for C, so we are going to update that, and the parent is also going to be updated to E. Okay, the other node that can be updated is F. The cost of F will be the cost of E plus 1, which is going to be 10. This is smaller than infinity, so definitely you would update it to that. The other node is G. G also can be actually updated, right? 9 plus 9, it is going to be 18. The other node is I. The cost of visiting I through E is going to be 9 plus 14, 23, which is definitely less than 104. So we are going to update the cost of I as well. The parent will be also updated. Okay, so from the node, at this point you just again check the priority queue. You ask the priority queue to give you the minimum, the item with the minimum cost that you haven't actually visited it, you haven't removed it before. Let me actually just put a marker here. These nodes have been already removed from the priority queue, so we don't, just to make it less confusing. So the next item that will be removed from the priority queue is going to be the node F. Let me just erase these parts. The node F with the cost 10. Let's use that color red. So the node F will be added to the tree. This edge will be added to the tree. Let me just erase this part. And through the node F, you can update a couple of nodes. you can update the node B. You can see that the cost of updating the node B is going to be 10 plus the cost of the edge F to B, which is going to be 8. So in total 18. But 18 is greater than the cost of B, which is already 15. So I'm not going to update the cost for B. The other node is H. So I can update the cost, the distance of H, which is going to be 10 plus the cost of visiting H through F. This is going to be 17. So in total, the cost for H is going to be 27, the distance. And the parent will be set as F. Okay, and no other node can be updated. So we are done here. So I'm going to mark F as already removed. Okay. The next item that can be removed from the priority queue is going to be the node C. Right? The cost of C is 12, and so this is going to be the best cost. So I'm going to add this edge to the tree. Okay, so this is not a part of the tree, remember. Okay, so for the node C, there are 3 edges going out. For each one, we are going to check that what would happen. C to B, so the cost for visiting B through C, this cost is going to be 2 plus 12, it is going to be 14. It is smaller than the distance of B that we already have, which is 15. So we are going to update 15, the distance for B. And the parent will be also updated. Okay. The other edge that we have from from C is the node F. Okay. We already know that the node F has been already visited, but I'm going to actually just discuss that what would happen in this case. If you wanted to visit the node F through C, the cost that you will get here is going to be 12 plus 6. The cost is going to be 18. This is definitely greater than the cost of F that we already have, which is going to be 10. And this is the exactly the idea behind the proof of optimality for the Dijkstra algorithms. All those nodes that have been already removed from the priority queue, it is not possible to add them again to the priority queue. The reason is that you already got a minimum distance for them and you removed them from the queue. If you find a new distance, so for example, just assume that this is the node F. You found some path to this node F, right? And you removed it from the priority queue. Now you find another node, for example, like C, that C has an edge to this node that has been already actually removed from the priority queue. The thing is, because you are visiting C after you have removed F from the priority queue, this cost here, this distance D of C, is definitely greater than the D of F. Otherwise, you would actually remove C before F, right? And because of that, adding whatever is the cost here is going to be, remember I emphasized on this fact that all the edges are going to be positive. So I already know that the cost of F, the distance of F is from the starting point is smaller than the distance of C. If you are going to add some other actually edge here, whatever is the cost here is going to be definitely greater than D of F. And the reason is that the cost of all the edges are positive. If there is any negative edge, you would see that because the cost can be here negative, it is possible to actually ruin this this inequation. Okay, but because we know that the cost is always positive in the Dijkstra algorithm, so this is the proof that basically shows us why if you removed some item from the priority queue, it's not possible to add it again. It's not possible to get any path with the shorter length. So this is actually the idea behind the proof. And again, you can also see here that from the node C, you can actually check the node D as well. D has been already in the priority queue and you removed it from the priority queue. It's not possible to get anything better, and it is clear the cost of visiting C is already 12 plus 18, 30. 30 is definitely greater than the cost of D, which is 5. So let me just erase all this here. Okay, let's get back to the algorithm. The node C has been removed from the priority queue as well. Let's check the priority queue and remove the node with the minimum cost, minimum distance, which is this time is going to be the node B. Okay, so, and what is the parent of that? That's going to be this edge. So I'm going to remove all these additional edges. They were not actually really a part of the tree, but anyway. Okay, so for the node B with the cost 14, there is only one edge going out. Through this edge you might actually update the cost of H, right? So whatever is the cost of B, which is 14, plus the cost of visiting H through B, this edge, which is going to be 12. This is going to be 26. This is smaller than the cost of H, the cost of H that we have. So yeah, we can get a better actually path for H through B. Okay. So the next node that can be removed from the priority queue, if you check, you will see that the next node is going to be the node G. This node will be removed from the priority queue. With the cost 18. The parent of G is E, so this is the edge that will be added. Okay. Through the node G, you might update two other nodes, H and I. The cost of H is going to be 18 plus the weight of G to H. This is going to be 25. Yes, this is smaller than the cost of H, which is now 26. So yeah, we can get a better path. Okay. The other node that we might update here is the node I. The cost of G is 18. plus the weight of the edge that goes from G to I. This is going to be 10, so the cost will be 28. This is already greater than the cost of I, so we are not going to update that one. So we are done with G. Again, we look at the priority queue and we remove another item from the priority queue with the minimum cost, which is this time is going to be the node I. So the node I will be added to the priority queue, and who is the parent? The parent is E. So this is the edge that will be added. Okay, through the node I, you can actually update the cost for, there is only one edge going out, that is the edge going to edge. So let's see that if we can update the cost of edge, that's going to be 23 plus the cost of I to edge, which is going to be 11. This is going to be 34, 34, sorry, which is going to be greater than 25, the already cost of edge. So we cannot update the cost of edge. And if you check the priority queue, there is only one item remain to remove, that is going to be edge. So this node will be also added to the tree, and the parent of edge is G. So this is the edge that will connect it. So let's clean up a little bit. And yes, this is the result of running Dijkstra algorithm over this example.